research is mainly in polymer material science. You did not guess what you're going to talk about tonight.
So I've been at Stanford since 1976, and for about 25 of those years, I only worried about research, only worried about polymer science. About 8 or 10 years ago, my wife, who is an artist, kept asking me about her experimental artwork, and she would do some mixed medias, either in the garage or her studio or out in the backyard, and she'd do something, there'd be some visual effect, and she'd say, why'd this happen? And so my background's in polymer science, interface science, organic chemistry, stuff like that. And so I would suggest what the cause might be. That then led to the creation of an introductory seminar. Stanford has a couple hundred of these things, wide variety of topics, almost any topic you can imagine. And this is a seminar that we've created, we've taught for 6 years now. Art, Chemistry, and Madness, the Science of Art Materials. So what I'm going to do is try to capture a little bit of the sense of this sophomore seminar. And then I do have an ultimate message that I'm trying to deliver in the class, and you can see if you can understand it at the end. And so, historical pigments. Before going into that, I'm not going to read this to you. I'll let you read it. It's in very large font. At about the time that we decided to create this sophomore seminar, there was a article, actually a whole series of articles in Chemical and Engineering News about chemistry and art. And this particular quote that I took out of this paper by Obiara, who is in the Material Science Department at Northwestern University, I thought absolutely captured the direction that I wanted to go from my part of this sophomore seminar. And so the question is there a divergence after the Renaissance of people that knew how to do art and that understood the sort of science behind it? So that's one of the things that I'm trying to explore in my part of the class. The key thing is probably up on
yeah, it's up here.
Yeah, so look up on the ceiling. On the ceiling is the bottom line for the way I look at art. A painting is a physical object. And so when I look at a piece of art, I don't understand the art history, I don't understand the meaning, I may not understand the political overtones, the religious messages, but I look at a laminated, stratified structure of multiple kinds of materials that respond differently to the environment. I look at the substrate, which could be rigid, it could be flexible. It is subject to maybe residual stress, environmental stress. Water, heat will cause potential changes in the dimensions down here. Depending upon the nature of the substrate, you may have a sizing that goes in to protect the substrate from, let's say, the binder that you're using that's in your ground, or maybe even down from the pigment layer. If I look at the ground layer, it could be white, as in this image. It could be different colors, depending upon the artist's intent with regard to what kind of reflectivity off the substrate did you want to have in order to transfer through the pigment layer to then see something of a particular effect. There are all sorts of mechanical aspects that are important for any one of these layers, mechanical properties. The pigment layer, which is what I'm going to talk about most, consists of a collection of inorganic pigments, organic pigments. They're all glued together with something. That something, by and large, is a polymer, right? And so I'm quite interested in that. That's really what drove me to think about this problem. On the top, there's perhaps a varnish, and it's subject to photooxidation. So this is my world. This is how I look at paintings. And in the sophomore seminar, what I try to do, this sophomore seminar, it's restricted to 16 students. 1/3 of them typically come from art history and studio art. 1/3 come from sciences and engineering. 1/3 come from the complete collection of Stanford students, international relations, human biology, econ, and so forth. And to begin, we see these images here that you probably have in a coffee table book at home. You've seen it on Discovery, you've seen it in Smithsonian. These are all examples of cave art, various famous caves. Altamira was one of the oldest ones discovered, but the most recent one is Chauvet. The interesting thing about all three of these caves is that they're all closed to public viewing. Okay? Why is that? That's because people exhale water. All right? And the lighting within the caves is also an element. So the issue with regard to having these fantastic images in caves, you can be thinking about why the people were in these caves in the dark with a tallow lamp, making these fantastic drawings. So there's no written record, so your guess is as good as anyone else's. But what did they make these drawings with? Well, ochres. And both these cores are from France. And the red ochre and the yellow ochre here, chemical composition. It's actually, red ochre is a mixture of an iron compound, hematite, and kaolinite clay. The yellow one here is goethite, or goethite, comes from Goethe, the German, and kaolinite clay. The darker versions, the siennas and umbers, have a little bit of manganese dioxide in them. But all of these materials are absolutely stable. They're permanent. They're not subject to photodegradation. They're not subject to chemical degradation. And so the ochres, as part of a palette that were applicable 25,000 years ago, are still applicable today. So let me look at some other substrates. So here's one substrate. It's in the wall of an Egyptian tomb. And so there's a wide variety of art that you can find. This is another sort of coffee table book. The palette for the ancient Egyptians didn't consist of very many colors. Red and yellow ochre we've already seen. Synthetic blue and green. This is sort of a glass frit material. Carbon black and gypsum white, and then later on some other ones were added. This iconographic kind of image brings in all sorts of interesting things to think about in terms of the stylistic approach that the ancient Egyptians used. For 3,000 years, the same images were used by and large. So the sort of picture book was kept, and it was mainly to tell a message that the cult of the dead. Another substrate is shown here in one of the houses in Pompeii that was covered by volcanic ash and the eruption in 79 CE. And so the red walls here is a particular material, cinnabar. Interesting background there. Another substrate, you may not guess this one. I may not get to it. The pages of an illuminated manuscript. Okay? What do these substrates have in common? All four sets of substrates. They're protected. They were protected at least for a period of time, long enough to wait for someone to go in and potentially look at those pigments to try to identify them. The prehistoric caves, okay? The cave art that was sealed off and then discovered in the last 100 or so years ago. The Egyptian tombs that were sealed off and also in a desert area. The house in Pompeii covered with ash. Inside the pages of the book that were certainly not subject to ultraviolet light, less exposure to other kinds of contaminants. All of these conditions were such that we can today go and potentially analyze what's in these pigments, such as using Raman spectroscopy. Well, here are some of the compounds that are part of the early palettes. And these are interesting materials. Orpiment, real, I love this name. Orpiment, realgar, cinnabar, and red lead. You'll notice my poison signs here. These are for real. So, arsenic, mercury, lead, these are all toxic materials. If you actually go through and look at the MSDSs, which is a sort of a list of things to think about for chemicals, the number of ways that you can get sick and die with these materials is very large. It's very gruesome. These are all bad actors. My headline was historical pigments, the good, the bad, and the ugly. These are definitely the bad, but this is a beautiful color. Just a beautiful, deep yellow. And the cinnabar is gorgeous red, okay? But the problem is these things are sort of embedded in other kinds of matrix material, and although you can break these apart and separate it to make the pigment, the way that they actually made the pigment from orpiment, these are sort of thermal hot springs kinds of materials with the sulfur, is to break it apart, heat it up, sublime it, Okay? So you sublime out the arsenic oxide, sublime out the mercury, and then recombine it. Turns out that the life expectancy of working in one of the cinnabar mines was low. The Romans used slaves, the Spanish used convicts, and it was a one-way trip into the mines. And so these are bad guys.
What about yellow cake?
That's another story. It's another story. So here are a couple of other colors. I love these very much. Malachite and the azurite. Turns out that the ancient Chinese palette was largely composed of the orpiment and cinnabar. We've seen malachite and azurite. So you see a lot of Chinese paintings where it's sort of flat field, not a lot of blending. These are the colors that are used. Same colors are used in Indian manuscripts. Okay, so it's not much of a guess with regard to how the trade went. The problem with azurite, even though it's a great color, it does have a tendency to degrade. Okay, and so this degradation here, it looks like it's turning into malachite, which you can see the chemical formula looks pretty similar. With regard to these pieces of information, the thing that's most important to the artist or who's ever grinding the pigment is how hard is the material. So talc has a hardness of 1. Diamond has a hardness of 10. It's on a log scale. Okay, so I mentioned earlier, and maybe that's on, so the Egyptian blue is basically a glass. It's a low temperature glass. It's not the same kind of glass formation. The ancient Egyptians had a great technology. They could make glass, they had a metallurgy, it was really quite sophisticated. And in this case, this is basically, it's called a frit, and it's a calcium copper silicate material, Egyptian blue. That had been around for quite some time, 2600 BCE. There's also material from the Han Dynasty called Han blue. If you look at this material, it's very, very similar. Starts out with the same copper source, malachite, add sand, add some sort of a carbonate. In this case, it's limestone, and here is barium carbonate. You come up with a material that's a barium copper silicate instead of the calcium. Very similar color. A lot of question in the scientific literature about, and there are people who make a living out of doing the chemical analysis of pigments, okay? And the thought is that these are indeed independent processes, although they're very, very similar, although separated by a couple of millennia. Other pigments that are available and have been available for a very long time, indigo. This is an example of indigo. Here's the plant. The East India Company made basically a living out of exploiting workers in India in producing indigo in 18th, 19th century. But here's the compound, indigotin, that is the source of this blue color. And what I want to do is to show you a little story now of sort of the universal reuse of organic compounds in different parts of the world and for different purposes. So this is indigo. And here, on the top of the board up here, Mayan Indians developed something called Mayan blue. And they discovered, presumably by accident, that if you had a fermenting vat of the indigo, there's 60 different kinds of indigo producing plants. In their region of Mexico, if you had this fermenting vat of the indigo, and there was a mixture of clay, why there would be clay, I don't know. However, that indigo, this molecule right here, a different kind of structure, would insert into channels in the clay. It's almost like a zeolitic structure. That insertion ended up protecting this very fragile organic material from heat. Okay? So this is basically an encapsulated organic compound. Here's a X-ray crystal structure showing these indigo inserted inside. Well, here's another one. So these are mollusks. These are shellfish. These are a murex kind of material. And my little map here that I've grabbed from somewhere. In the class, I get full attribution for all of my images, but I don't have it here. So here's the Silk Road in the trade. Along it, there's one spot right here, right on the shore of the Mediterranean, where the Silk Road went down here and then went up to Venice by water. And at this location, these shellfish were harvested by huge amounts, just huge amounts. These are only, you see the scale by here, 2 centimeters, so like 8 centimeters long. There's a little gland inside that you can separate by macerating the material, and that gland produces something called Tyrian purple, and this chemical structure, I don't ask you to remember it, but it's the same as indigo, with this little X prime, that's bromine. So bromination, same material, different parts of the world. Another ancient dye, in this case is madder, and it comes from the plant. Here's the chemical compound here, and this is a particular one, alizarin. And the one thing I want to point out here is that many of these synthetic materials were produced chemically, typically in the 19th century. And so there is a synthetic indigo, there is a synthetic alizarin, there's no synthetic Tyrian purple. But here's another way of thinking about the same kind of organic chemistry in a different context. Turns out that there is a scale insect. In Europe, it's called Kermes. In Mexico, it's cochineal. And these little scale insects live in sort of little foam-like, these are wild ones here. They're actually cultivated. Little bitty baskets that the scale insects grow in, and then they're harvested. Here are the insects. The eggs have been laid. Eventually, these things are dried out and ground into powder. Same chemical structure, with the exception that this one little ring here is deglycosylated. It's removed. Talk about pigments, good, bad, and ugly. We've seen bad, okay? Here's the good, okay? Lapis lazuli. This is a rock. It's a mixture of 3 components. Lazurite, the blue material, calcite is white, iron pyrites is the yellow part here. Now if you just take it comes in Afghanistan up in the mountains. If you just take this material and grind it up, you get a really, really crummy pigment. It's sort of gray, it all grays out. The problem is that you have to separate the blue material from the rest. And here's what Chinini said about this color. He loved ultramarine, the color illustrious, and so forth, most perfect. Here is the process that was developed to remove the blue from a mixture. Complicated process, took like a month, basically a combination of surface chemistry and wetting phenomena in order to get the material. Okay, finally, we're moving into a period where I'm going to stop because at this point, we have, or up to this point, the artists have ground their own pigments. Well, they may have had people in their studio that ground the pigments, but they were in charge. The artists were in charge. Round about this time, the question of separation of the artist and the technology began to diverge. Okay? Here's the palette that Jan van Eyck was using in this particular painting. These are all ones we've talked about, a couple of new ones, small, verdigris, and lead tint yellow. But the newest thing, the thing that really made the difference with regard to applicability was these kinds of compounds that were part of drying oils. And so Jan van Eyck didn't invent oil painting. He certainly popularized it and did it very well. But these chemical structures in here end up cross-linking, and that's what makes the oil dry, the binder dry. All right, so those were the good times. In 1801, where is it? That's up on the top. In 1801, here's a list of all of the watercolors that were sold at one particular location on the Strand in London. And of this list, 2/3 of them were non-permanent or toxic. Okay? Because in the period after 1500 or so, there was really an explosion of chemistry, an explosion of sort of entrepreneurship in terms of lots of people making lots of stuff. And indeed, there are many, many different materials that were included. The one that's not on here, Sarah pointed out to me, is mummy. In fact, there was a pigment, ground up Egyptian mummies. This was sort of state of the art. You know what? Now, most of these, either not good for you or they didn't last very long. Now, other things have come along since then. For example, here's a range of compounds. These are cadmium compounds. These are really beautiful materials. It's a various measures of cadmium sulfide, cadmium selenite. You get all sorts of different colors. The Impressionists, or Monet, certainly liked cadmium yellow, one of his favorites. Now, chromium compounds. Chromium was discovered about the same time. Chromium gives some really beautiful colors. The problem is that both chromium and cadmium are implicated today in potential carcinogens. Okay? And so they're not banned. They're not banned yet. They likely will be. So, what have organic chemists done for contemporary art? Most materials today, you go to your favorite art store if you purchase art materials, most of them are organic compounds. Okay? There'll be different binders. It could be acrylic binder, for example. But the quinacridones and the phthalocyanines are probably the big actors right now. You can tell, if you wish, what's actually in the pigment that you, Winsor & Newton pigment that you buy. It'll say PB14. Pigment blue 14 will be identified by chemical name in terms of what's in it. And so you can get these lists. You can go to the Winsor & Newton website and you can get them all. They won't tell you how much is in a blend, okay, but they'll tell you what the content is. So, with that, I'm at the end of what I wanted to say. Pierre, do I have any time left? Okay. I now want to switch gears a little bit and show you a little bit more about our class, okay? First thing I want to do, one of the things that we have found fascinates students is looking at small stuff, okay? And so I had a postdoc, Ben Muir, who really liked to do scanning electron microscopy. So this is a pencil lead, all right? And it's a number 2B, as you can see on the roof. It's a number 2B, and there are different degrees of you'll see that this is a mixture of graphite, which is a planar compound, and clay. And if you look at these various cross-sections, you'll see there are plate-like structures here, but they're sort of twisted and curved. That's because this mixture of graphite and clay is extruded through a die to get a little sort of pencil lead, and then you put the wooden case around it. So that's what a pencil looks like inside. This is vellum. So it is a it is either parchment. Sarah, tell me, parchment is what animal? Sheep, okay. Or calf or vellum. And what here's the hair side, the follicle side. Here's the bottom side of the vellum, where you can see the fibrils here and different degrees of magnification. Here's what happens when you try to tear it apart. It's very, very difficult to tear it apart. Sarah's a calligrapher. She does work on vellum. And so some of this stuff is very, very precious material. And so this is what it looks like inside. Here's another one. So this is a semi-classical gypsum. So it's rabbit skin blue, gypsum, marble dust, titanium dioxide. This is obviously the new element that's in here. The point of this image, this is 2 microns. Your hair, if you have hair, your hair is 100 microns in diameter, okay? Thereabouts, 50 to 150. This is 2 microns. These are very small particles. And so here are some of it's either marble dust or some titanium dioxide, but it's been pulled out of there. And then finally, this is a lake pigment. This is a rose madder gouache. And you can look at, and we've done this, a whole series of electron micrographs of various gouache materials, and they all look the same. The reason they look the same is that they're so-called lake pigments, which means that you take a dye molecule and you precipitate it on top of an inorganic substrate. And the inorganic substrate is all the same. Okay, the last quick section of slides. Our class does field trips, and Sarah runs all this. Field trips to the Rare Books Room at Green Library on campus. There are calligraphy lessons that Sarah teaches. And some of these folks, and see, they're working with quills, some with And they grind pigments. Grind pigments with egg yolk, egg tempera, or oil. Okay. Note the masks, note the goggles, note the all that stuff. How many of the artists wear masks and goggles? Okay. And they just try things out. There's no intent. There's no need to make anything that's artistically attractive. But these are some of the results. And they do make paper. Paper turns out to be a lot of fun because you make a big mess, and ultimately the things are usually work out. Except for this young lady right here, she's not happy with that particular version. Okay, that's it. Thank you.